Okay, hello again. Welcome back to the next video in this series. Now, we've talked about gravitational potential energy, we've talked about kinetic energy. Today, then, we're looking at this next type of energy called elastic potential energy. Now, again, I'm sure you've heard of this before when you were talking about energy stores. We're just going to look at it in a bit more detail. I do very quickly, first of all, though, just want to recap something that you did back in the forces topic, because it can come up again in this type of question. And also it's a good chance just to do a bit of recap. So I just want you to remember what we get if we're thinking about a stretched or compressed actually, but normally a stretched object. And you would have done this in the context of springs, and you talked about Hooke's law. And we had a formula that is to do with the force required to stretch a spring or another object. And if you remember, the formula was force equals spring constant multiplied by the extension of the object. So that's how much longer the object is than when it started. So for a spring, how much longer is it than its original length? And we could check the units for that just to remind us here. Force is measured in newtons, extension is measured in meters, and using a bit of logic there, you can work out that the spring constant must be measured in newtons per meter. Now, it's a good opportunity to recap this idea of spring constant. Just means really how difficult is it to stretch the spring. Okay, now it actually means how many newtons does it take to stretch the spring by 1 meter. So a spring that has a spring constant of 2 newtons per meter, that means it takes 2 newtons to stretch it 1 meter. Okay, now we're going to need this idea of spring constant later, which is why I wanted to recap that formula. And as I say, the more times you see it, the more familiar you'll get with it. Remember, this is one of the equations that you need to learn for your exams. Now, going back then to what our title is, elastic potential energy, and thinking about a definition for it first of all. If we think about this idea that we've just written down about a force, if you are applying a force to a spring, a force is being applied, it's stretching the spring, that means work is being done. And as you remember, work done means energy transferred by a force. So energy, therefore, must be being transferred. And so where's that energy going? Well, that energy is being stored as elastic potential energy. So it just means the energy stored by a stretched or, in fact, compressed object. Now, all this time, we will be using extension, and you see we were up there. If you were compressing an object, you would just use the compression instead. It's exactly the same formula. Okay, right. Let's look at our formula then. So, elastic potential energy equals. Now, the format of this is almost identical to the kinetic energy formula. Okay, so in terms of the maths and how you work stuff out, it's pretty much the same as kinetic energy. So if you remember, kinetic energy was half times mass times speed squared. If you can't remember that, I will put a link about there to the video that you can go back to. So elastic potential energy equals half times, well, it's not times mass, it's times spring constant times the extension squared. Okay, now like with kinetic energy, it's only the extension that is being squared there, not the whole thing. So you might sometimes see brackets around the extension just to show you that. All right, units again then. Elastic potential energy, well, it's energy, so it's in joules. Extension, that's measured in meters. And spring constant, like we said earlier, is in newtons per meter. Now, I will show you this in symbols. As you know, I'm not a great fan of using symbols, but I will show you what they are just so you've seen them. So elastic potential energy is given the symbol capital E and then a small e as a subscript. So that's standing for elastic energy, basically. Equals half spring constant given the letter K, extension given the letter E. Now you can see there why I say don't use symbols, because if you forget that spring constant is a K, or you forget that elastic potential energy is capital E and small e, you run the risk of losing marks. Now I will say though, this formula, good news, is actually given on your formula sheet, and it is given on the formula sheet in symbols as well. So for this one, just to save you time, you may want to write it out in symbols. That's absolutely fine as long as you use the correct symbols. Right, let's look at a couple of examples then. Usual thing, and do a bit of practice. Okay, here we go then. Here's a question. Sorry you can't quite see the number 1 on the left-hand side, but I'm sure you can work out what a number 1 looks like. So, a spring has a spring constant of 100 newtons per metre and is stretched by 20 centimetres. Find the energy stored. Okay, relatively simple as long as we're careful. First step, as always, write out the formula. So I'm going to do that now. All right, there we go. Sorry, it's a little bit messy. So, let's see what we're doing then. Right, we're trying to find the elastic potential energy. So, half times spring constant, that's 100. Extension, 20 squared. Now, hopefully you are all shouting at your screens now that I've made a mistake. And now, it's a very common mistake, and you know what, would probably only cost you 1 mark, but we don't want to be losing even 1 mark. It's this 20, look. 20 centimetres. Okay, 20 centimetres, we've got to put that into metres. Now, hopefully you remember 100 centimetres in a metre, divide 20 by 100, we get 0.2 metres. So actually, the number that needs to go into here is not 20, it is in fact 0.2. So there we go. Here is our calculation we've got to do. Now, you could put that into a calculator. Half times 100 times 0.2 squared. The answer you actually get when you do that is you get 2 joules. Okay, I mean, you could break this down further if you wanted to. You could simplify this. Half times 100, which is 50. 0.2 squared is 0.04. 50 times 0.04 is 2. Okay, but as long as you've shown here the substitution of the numbers into the question, that's the really key bit. Okay, let's have a look then at another example, just one more, and then I'm sure you will have a go at some questions. Right, a couple of things to notice. You might be looking at that going, but there's only one number. Yes, that is true. This, though, is the key bit, the same spring. Okay, if it is the same spring, that means it has the same spring constant as the previous question. So, although I've got rid of it, hopefully you can remember that the spring constant before was 100 newtons per metre, and obviously in an exam question, if it said that, you'd be able to look back at the previous question. It does bring up a general exam tip, really. If you're looking at it thinking there's only one number, maybe you've calculated the value you need in a previous question. For example, the previous question might have used that formula to work out a spring constant. And then this question could be the second part of it, and actually you'd have to use that spring constant that you've just worked out. So just think about what it is you need and have a look. Maybe you've worked it out before. In this case, though, we were given it in the previous question. Okay, right, we're going to write out the formula then. So I will get on with doing this. You don't want to sit watching me do it, so I might go into my super speedy writing again. All right, there we go. Again, sorry, seem to be getting messier and messier with my handwriting here. Right, start to substitute some numbers in then. Elastic potential energy we know is 5. So we've got 5 equals half times spring constant, we know is 100, times the extension squared. Now the question, remember, is how far is it stretched? So we're looking for the extension. All right. Another general tip, I guess, when you're doing questions like this, make sure the number you're given or looking for is extension. They might throw in an original length, so just watch out, make sure it really is the extension that you're checking, that you've got. All right, so let's do a bit of simplifying. Well, on this side, on the right-hand side, I can simplify this. Half times 100 is 50, so 5 equals 50 times extension squared. Okay, well, here's what we don't know. 5 equals 50 times that. Think maths. If I want to get extension on its own, I need to divide by 50. Now I am going to use the brackets like you might do in maths just to show what you're doing. So I'm dividing both sides of this equation by 50. 5 divided by 50 is 0.1. You can check that on your calculator if you need to. And so on this side, the 50 has gone. So I've got 0.1 equals extension squared. And so hopefully you can see then if I actually want to calculate the extension, I need to find the square root of 0.1. So I've effectively square rooted both sides. And if I do that, I get an answer of, let me just stick it into the calculator, I get an answer of 0.32 if I round it to 2 decimal places. So 0.32, and it's an extension, so that's going to be in meters. You may, of course, write that as 32 centimeters. Okay, you'll be pleased to know then that's actually the last new formula for this section. In the next video, we'll kind of be bringing it all together, all the stuff we've done over the last few videos, bringing it together to see how they can link it together in questions. But until then, stay safe, have fun, and I'll speak to you soon.